Hi. In the last part of the vapor and combined power cycle lecture, we are going to talk about the cogeneration system and the combined power cycle. Let's talk about the cogeneration system first. The cogeneration system is the system which can be used to produce both heat and power. Okay, both process heat and electrical power. Okay, so you can see that the form of energy which can be used would be in both heat and power here. Okay, now in the Rankine cycle, you can see that we can split the steam that we produce from the boiler. Okay, we can split the steam here. Instead of put all the steam through the turbine, you can split some amount of the steam, okay, to be used in the process heater. Okay, so in this case you get benefit from the heat to be used in the process, and you also get the work that generates from the turbine as well. Now in the process you may need the steam at a lower pressure. You can then extract some amount of steam at intermediate pressure using an extraction turbine. Okay, this intermediate pressure steam can be used in the process as well. Okay, for this kind of system which can produce both heat and power, the performance index is now called a utilization factor. Okay, utilization factor also use the same concept as efficiency in the calculations. Okay, utilization factor is defined as what we get divided by what we give as well. But in this case, utilization factor is the net work output plus the process heat that the system can deliver. Okay, so we have benefit in both terms, the work and the heat. Okay, net work output plus process heat delivered to the process divided by the total heat input to the boiler, total heat input that we supply into the boiler here. Okay, so utilization factor or EU here will be equal to W net plus QP. QP here is the process heat, okay, deliver, divided by Q in. Okay, this is the definition of the utilization factor. Now let's have a look at the example of the cogeneration system. Okay, we have a cogeneration plant which can be used to generate both power and process heat. We consider an ideal cogeneration steam plant. An ideal cogeneration steam plant. Okay, the condition of steam, okay, which enter the turbine is at 7 megapascal and 500 degrees Celsius. We also have the mass flow rate of the steam in this cycle at 30 kilogram per second here. This is the mass flow rate, m dot here. Now in this system we will extract 1/4 of the steam from the turbine. 1/4 of the steam from the turbine will be extracted. So 1/4, it means that 25%, okay, of the total flow of the steam in this system will be extracted from the turbine, and it will be extracted at 600 kilopascal. Okay, extracted for process heating. Okay, and the remainder of the steam, the remaining amount of the steam, that would be 75% of the total flow. Remainder means 75%. Okay, it will continue to expand in the latter part of the turbine, and then it will exhaust to the condenser at 10 kilopascal. Okay. The steam extracted for the process heater is condensed in the heater, and then it will be mixed with the feed water at 600 kilopascal as well. Okay. The mixture here will be pumped back to the boiler pressure of 7 megapascal. In this example, we are going to show the cycle on a TS diagram with respect to the saturation lines, and also determine the following parameters. We want to determine the heat transfer from the process heater per unit mass leaving the boiler. So we want to determine Q process. Okay, Q process. We have the answer for the heat rate to the process, or Q dot process here, at 15,774 kilowatt. Okay, we want to determine small q delivered to the process here, Q per unit mass. Okay, unit mass of the total steam. We also want to determine the net work produced by the cycle. Okay, net work produced by the cycle. The answer is here 32,848 kilowatt. And lastly, we want to determine the utilization factor of this plant. So it would be 52.4%. Okay, and Q in to the cogeneration plant would be 92,753 kilowatt. These are the answer to all questions. Okay, now I'm going to show you how we obtain this result. Okay, in this example, we have some information provided, okay, from the problems. Okay, you can see that we know condition at number 2. Okay, you know enthalpy at number 2, you know enthalpy at number 5, number 6, 7, and 8. Okay, so you know the enthalpy at several points. Okay, so you have to determine the enthalpy at point number 1, number 3, and number 4. Okay, 1, 3, and 4. Right? They are the value that you need to know first before you can do the energy balance to calculate the work obtained from the turbine, to calculate the Q required in the boiler, or Q provided to the process in the process heater, for examples. Okay. Now let me draw the cycles on the TS diagram first. Okay. In this diagram, as I have already explained to you, that we know the condition of number 1. Number 1 is at the sat liquid, so it is also known number 1. Number 2, enthalpy is already provided. Okay, and number 5, okay, number 5 is already provided as well. Number 6, 7, and 8. Okay, we know 5, 6, 7, and 8, and also number 2. Okay, and number 3 as well. Number 3 is actually at the sat liquid, so you can determine the enthalpy at number 3 as well. Okay, so the cycle, the cogeneration cycle, will operate with 3 different pressure level. The high pressure here, high pressure here would be at 7,000 kilopascal. Okay, and we also know the temperature at this point, T6, is 500 degrees Celsius. Okay, at intermediate pressure here, we know that P7 is at 600 kilopascal. Okay, and at low pressure here, we know that P8 is at 10 kilopascal. Right. Now the other information that we know is that the flow rate in the boiler, if we assume that it's 100% or the full fraction of 1, okay, it will expand in the first part of the turbine with the full fraction as well, 1. It will be extracted for the process heater. This is the extraction part to be used in the process. Okay, from 7 out at number 3 here, this is a part of the steam to be used in the process. So it will be extracted with 25% amount, 25% of the total flow. And the remaining part will expand further to the exhaust steam. Okay, so it would be 0.75 or 75%. And then after that, this remaining part will be condensed in the condenser. So the flow rate through the condenser would be at 75% of the total flow as well. Okay, so you have the boiler from 5 to 6 here. This is boiler. From 7 to 3, it would be the process, heat for the process. From 8 to 1, it would be condenser. Okay. Now, the sad liquid from the condenser, it will be pumped up to intermediate pressure to number 2. Okay, this is a pump. Okay, and then the liquid from the first pump will be mixed with the liquid, sad liquid from the process. So 2 mixed with 3, it would be 4. Okay, 2 mixed with 3, it would be 4 here. 2 and 3 mixed together, it would be number 4. And number 4, it will be pumped from intermediate pressure to the high pressure at number 5. Okay, so this point would be number 4. Okay, the mixing point here. Right. So the cycle of the cogeneration would be as shown here. Okay, you got information provided by the problems. Okay, you also know that the mass flow rate, okay, of the steam leaving the boiler is at 30 kilogram per seconds, or M6 equal to 30 kilogram per second here. All right. So we want to know, what we want to know is Q process. Okay, what is the Q process? Q process here is the heat rate, okay, delivered to the process per unit mass of the total steam, which is M6. Q process here equal to heat rate, okay, provide to the process divided by M6. We also want to determine W net, okay, net work output. And we also want to know the utilization factor, EU, for this cogeneration system. Alright then, let's move on to determine the answers to the first question. What is the Q process. Okay, so for the Q process, you have to consider the heat provided to the process. Okay, in the process heater. Okay, in the process heater. Okay, you have steam from the extracted from the turbine. Okay, number 7. Okay, and provide heat to the process, it will come out at number 3. In the process, you may have some process stream. This is the process stream. Okay, so we want to know the heat, okay, that we can use to deliver to the process stream. So we want to determine this amount, this Q process here. Q process here. So Q process can be determined from the energy balance on the hot stream. So Q process, or the heat rate provided to the process, equal to Q73. Okay, then that would be M7 multiplied by H7 minus H3. Okay, M7 here. M7 is the amount of steam that you extract from the extraction turbine. So M7, okay, equal to 25% of the total flow. So you have 25%, 0.25 multiplied by 30 kilogram per second. This is the total flow. So M7 here is 7.5 kilogram per second. Okay. Now you already know enthalpy at point number 3 and enthalpy at point number 7. Okay, so you can calculate Q73 easily. Okay, Q73 equal to 7.5 kilogram per second multiplied by H7 to 773.7 minus 670.38, okay, kilojoule per kilogram. Okay, so the number would be 15,774.9 kilowatt. Right? Now we want to determine the Q provided to the process per unit mass of the total steam. Okay, Q process here would be Q73 divided by M6. Okay, M6 is the total steam flow. So that would be 15,774.9 divided by 30 kilogram per second. And the result would be 525.83 kilojoule per kilogram of total steam flow. Okay, so this is the first answer. Okay, now let's move on to determine the network output. Okay, in this system you can see that the network output can be calculated, okay, from W turbine minus W pump, but you have two pump here, so it would be minus W pump 1 and minus W pump 2. Okay, you have 2 pumps, right? So to determine W net, the rate of the power here, okay, you have to determine each term, the turbine work, the pump work for number 1, pump work for number 2. Okay, let's determine the turbine work first. Determine turbine work. Okay, we can do the energy balance, okay, around the turbine. Okay, so we draw a sketch of our extraction turbine here. Okay, you have the flow rate coming in at number 6, which is at 30 kilogram per second. Okay, the first extraction point would be at number 7. The flow rate at this point is at 7.5 kilogram per second. Okay, and the final exhaust point would be at number 8. Okay, with the flow rate of 22.5 kilogram per second. And you have the turbine work output here, W turbine. Okay, so you can write the energy balance, energy in, energy flowing in would be equal to energy flowing out. Okay, energy flowing in would be M6 H6 equal to energy going out, that would be M7 H7 plus M8 H8 plus the turbine work, W turbine. Okay, now you can rearrange this equation to determine W turbine. W turbine would be M6 H6 minus M7 H7 minus M8 H8. Okay, you know the value of every parameter here, every variable here, M6, M7, M8, H6, H7, and H8. You know everything, so you can just substitute all the values into this equation. So you have 30 multiplied by 3410.3, okay, minus 7.5 multiplied by 2773.7, and then minus 22.5 multiplied by 2153.2. Okay, and the answer for turbine work would be 33,059.25 kilowatt here. Okay, so this is the turbine work. Okay, now let's calculate the next term, the work required for the first pump and for the second pump. So we will determine the work required for the first pump, determine W pump number 1. Okay, we can do the energy balance around the first pump. Okay, the flow coming in at number 1, the outlet coming out at number 2, and you need power to drive this pump, W pump 1. Okay, the flow rate through this pump would be 22.5 kilogram per second. Okay, so the energy balance around this pump, you can then calculate W for pump 1. W for pump 1 would be M2 H2 minus M1 H1. In this case, you can see that we have only one single inlet and single outlet. So M2 and M1 would be the same. Okay, so you can just write M1 multiplied by H2 minus H1. You know the value of every variable, so you can just substitute M1 22.5, H2 192, H1 191.8. Okay, so the work required for the first pump would be 4.275 kilowatt. Okay, now you can do the same thing with the second pump. Okay, determine the work required for the second pump. Determine W pump 2. Okay, so you can do the energy balance around the second pump. Inlet would be at number 4, outlet would be at number 5. Okay, with the pumping work required, W pump 2. Okay, the flow rate to this pump would be at 30 kilogram per second. From the energy balance around this pump, you can then write W pump 2 equal to M5 H5 minus M4 H4. And in this case, with single inlet and single outlet, mass flow in would be equal to mass flow out, M4 equal to M5. So you have M4 multiplied by H5 minus H4. You know everything. 30 kilogram per second for M4. H5 is provided by the problems, 318.53 minus H4. H4 is at what? We have to determine H4 first. We don't know H4. Now we have a problem here. So you have to determine H4 first, okay, in order to calculate the work for the second pump. H4. Now, how do we calculate that? We can determine H4 by doing the energy balance around the mixing point. Okay, determine H4, okay, from the balance around the mixing point. Okay, determine H4 from the balance around the mixing point. Now at the mixing point here, you can see that we have two inlets. Okay, the first one is number 3, which is at 25% of the total flow. The other one would be number 2, which is at 75% of the total flow. And the outlet would be number 4, okay, with the flow of 100%. Okay, so we assume that the mixing point is adiabatic. Adiabatic mixing. So it means that we don't have any heat transfer between the system and the surrounding. Okay, we can then just write the energy balance E in equal to E out. Okay, so we have M2H2 plus M3H3 equal to M4H4. Okay. Now we want to determine H4. Okay, we don't know H4. We know H3, we know H2. So we can use this balance to determine H4. Okay, so we write H4. That would be M2 divided by M4. Okay, H2 plus M3 divided by M4 H3. Okay, so you know the fraction M2 would be 25% of the total flow, or M4. Okay, so the first fraction term would be 0.75. Okay, multiplied by H2. You already have that value from the problem, 192, plus M3 over M4 would be 25%, or 0.25, multiplied by H3. You already have that as well from the problem, 670.38. Okay, 670.38. So you can then determine H4. H4 would be 311.595 kilojoule per kilogram. Okay, kilojoule per kilogram here. Now, having obtained H4, you can go back to calculate the W pump number 2. W pump number 2 would be equal to 30 multiplied by H5, which is 318.53, minus H4, we just have it here, 311.595. And the pumping work required for the second pump would be 208.05 kilowatt. Okay. Now you have everything you need. Okay, so you can then calculate W net. W net equal to W turbine. You have the value 33,059.25 kilowatt, minus W required for the first pump, that would be 4.275, and minus W or work required for the second pump, 208.05 here. Okay, so the net work output would be 32,847 kilowatt, and that would be your second answer. Okay, net work output 32,847 kilowatt here. All right. Now we will calculate the utilization factor, but we need to calculate the heat input first. Okay, so we will determine Q in first. Determine Q in. Okay, so Q in can be calculated from the energy balance around the boiler. Q in would be M6 H6 minus M5 H5. Okay, M6 H6 minus M5 H5. You can substitute out the value 30 multiplied by H6, which is 3,410.3, minus H5 318.53. Okay, so the heat requirement for this cogeneration system would be 92,753.1 kilowatt. You can finally calculate the utilization factors. Okay, determine EU. Okay, so from the definition, EU can be calculated from W net, what you get plus what you get in terms of the heat to the process, Q process, and divided by total Q in. Okay, Q in here. So by substituting all this term, you have 32,847 kilowatt for W net, 15,774.9 kilowatt for the heat to the process, and divided by Q in, which is the value that we have just calculated above there, 92,753.1. And the answer for utilization factor would be 0.524 or 52.4%. Okay, so this is your final answers, okay, for the utilization factors. Right. Now, I also have another system, okay, another complex system, which is normally used in the power plant today. Okay, this system is a combined system, so we call that a combined cycle. It's a combined cycle which consists of the gas turbine cycle and the steam turbine cycle. Okay, so it means that we combine the Brayton cycle and the Rankine cycle together. Okay, so in this combined cycle, you can see we have the gas turbine cycle up here. So the cycle at the top here would be called the topping cycle. But the cycle down here is the steam turbine cycle. Okay, we will call this cycle the bottoming cycle. Okay, now you can see that for the gas turbine cycle here, you have the waste heat. Okay, this is a waste heat from the turbine exhaust that we already know. If we release this exhaust gas to atmosphere, this amount of heat will be wasted. Okay, so instead of releasing the exhaust gas to the atmosphere directly, we will use the exhaust gas to boil the water. Okay, so we use the exhaust gas in a heat exchanger. In this heat exchanger, we will have a heat transfer between the exhaust gas and the water. So water will be turned into steam, and then we can use that steam to drive the steam turbine to get more work. Okay, so this kind of heat exchanger will be called the waste heat boiler. Waste heat boiler. Okay, and the other name for waste heat boiler, you may also call it the heat recovery steam generator. Heat recovery steam generator. Okay, or HRSG. We can call it HRSG. Heat recovery steam generator here. Okay, so you can see that in this combined cycle, you have the gas turbine cycle working together with the steam turbine cycle. You get work from both the gas turbine and the steam turbine. Okay, you have W here, okay, from the gas turbine cycle, and you also have W net here from the steam turbine cycle as well. Okay, so you can see that you can use only the heat supplied to the combustion chamber only. Okay, so the heat input would be just through the combustion chamber. You don't need any more heat to boil the steam. Okay, to boil up the steam in the Rankine cycle here, you can use the waste heat from the gas turbine cycle. Okay, so in this case, the thermal efficiency of the combined cycle will be higher than the gas turbine cycle alone, and it will be higher than the Rankine cycle alone. Okay, so for the state-of-the-art power plant that we use to produce electricity today, they are normally the combined cycle. Okay, and normally in practice, okay, we don't use one gas turbine cycle to work with one steam turbine cycle. Normally we will use the ratio of gas turbine cycle to steam turbine cycle at the ratio of 2:1. It means that we will use 2 cycles of gas turbine to work with 1 cycle of steam turbine. Okay, 2 cycles of gas turbine. Okay, we will get the exhaust gas from these 2 cycles, and we use the exhaust gas from 2 cycles here to boil up water in 1 steam turbine cycle. So it would be called 2:1 configuration. 2 gas turbine cycle with 1 steam turbine cycle. Okay, in some design it may be 3:1. It is possible as well. 3:1 is also possible. 3 gas turbine cycle with 1 steam turbine cycle. Okay, and that concludes everything that I want to explain or describe about the vapor and combined power cycle. This is the last part of this lecture. Okay, see you next time in the next lecture. Goodbye.